All right. So this section is again on the derivatives of the trig function. So I've got a little paragraph right here, and we're actually going to do this in kind of a unique way. In most calculus books, along with the section where you do finding the derivatives of the trig functions, you also learn how to find some limits involving trig functions. And we've done a couple of those, and I'll remind you of those, but then we're going to do some that are a little bit more interesting and show a fairly valuable trick that's used in quite a few places in math. So let's take a look here. So when we're done with chapter 3, you'll need to be able to differentiate nearly any function. Okay, so that's what this entire chapter is about, is just adding to our bag of tricks, finding derivatives of any type of function. So we've done the exponential function, we've done power functions, we've done products, quotients, sums, differences, constants, all that sort of stuff. Okay, so we'll need to be able to find the derivative of any function that we're presented with. We'll also need to understand what the derivative means. Okay, in other words, what's its interpretation? And we'll need to be able to blank that meaning to real-world problems. So we'll need to be able to apply. Yeah, we'll need to be able to apply that meaning to real-world problems. Okay, so again, in section 3.3, we're going to add trig functions. And again, we're going to start off with limits. And we're going to approach the derivatives of trig functions, both from the definition, finding the limit of that difference quotient. And then we're also going to review, again, at the beginning here, some general limits finding that involve trig functions. So if you'll remember from chapter 2, if I'm finding the limit as x approaches 0 of the sine of x over x, what was that limit again? It was 1. Okay, and it really wouldn't matter what variable I put here. I could put a u here, so if it was the limit as u approaches 0 of sine of u over u, it would still be 1. This is kind of like a dummy variable, so I could change that quantity to be anything I wanted to, okay? And we also talked about this one right here. This the limit as x approaches 0 of sine of x, or excuse me, cosine of x minus 1 all over x. Anybody remember that one? That one was 0, okay? So again, you'll notice that in both cases, if you were to do this by direct substitution, you have a 0 on the top and a 0 on the bottom. In this case, you get 1, and in this case, you get 0. So that quantity, 0 over 0, is really hard to pin down. Sometimes we get a number, like 1 or 10 or 22. Sometimes we get 0, okay? And sometimes we'll get something that's undefined. And we'll actually spend some time talking about limits of that nature later on in the course, okay? But we can actually use those. If you'll keep those familiar limits in mind, we can actually use those to find some limits that are a little bit more complicated. So let's take a look at this problem right here. It says the limit as x approaches 0 of sine of 5x over x. And the format of that limit is similar to, but not exactly like this one right here. Okay, so like I said, it's a dummy variable that we put here. So for all intents and purposes, I could put a school bus right here. And I could say, what's the limit as the school bus approaches 0? Sine of the school bus over the school bus, and it would still turn out to be a 1. Okay, the point here is every single one of these quantities is exactly the same expression. Well, if I look at it on this one, x is approaching 0, that's an x. That's what I'm used to. What I'm not used to is having a 5 right there. And we want to figure out what happens there, okay? So what we do is we use a familiar technique, okay? A technique that you've seen before. It's called substitution. So what I'm going to do is I'm going to say u is equal to 5x. So I'm going to change this that looks a little bit unfamiliar into something that looks more familiar. Now, what we're interested in here is the behavior as x approaches 0. So as x approaches 0, 5 times 0 also approaches 0. 5 times 0 also approaches 0. Or 5 times x also approaches 0. Okay? Well, if this approaches 0, and these two things are equal to each other, then that must also approach 0. So what we're going to do is we're going to change the variable of the limit. So I'm going to change this to the limit as u approaches 0. Okay? And wherever there's a 5x, what can I put? I can put a u. So this is going to be the sine of u. And then in the denominator is an x. Okay, now this is another helpful skill that you want to get used to. Okay, all those algebra techniques that you learned up until now, those are still valid. So if this is an equation, I could take that an equation and I could say, well, I want to know what x is. Well, x is u over 5. I just took both sides, divided it by 5. So that means wherever I see an x, I can put a u over 5. So let's put a u over 5 right here. Again, I haven't done anything calculus-wise. All I'm doing is changing the expression in the variable, in the limit. So if we take a look at this, this is now a complex fraction. We normally wouldn't write it that way. I'm going to take this and I'm going to flip it over and I'm going to multiply. So this would be a 5 on the top and a u on the bottom. So now I'm going to change it to this. I'm going to change it to the limit as u approaches 0. I'm going to pull the 5 out front and I'm going to write the sine of u over u. And I'm even going to put a set of parentheses around that. Now, algebraically, is that a totally okay thing to do? It is. And if we technically use the limit laws, the constant multiple rule, I can actually take this and I can slide this out front. So I'm going to take that and I'm going to put it out here. Now, take a look where we started with something very unfamiliar, and take a look where we are now. I have the number 5 out front times some result of a limiting process. And let's take a look at this. Limit as u approaches 0, sine u over u. What is that? That's going to be a 1. So what's my answer to this problem? The answer is 1. So if I were to rewrite that, oh, sorry, 1 times 5. Thanks. Getting ahead of myself. Limit as x approaches 0, sine of 5x over x. That answer is, oops, I should have changed colors here. X approaches 0, sine of 5x over x, it equals 5. Okay, so there's our answer. Any questions there? So we use this technique of changing variables, making a substitution, so we can change something that looks unfamiliar into something that looks more familiar. So let's take a look at this one here. Again, the idea on the previous one was we wanted to make this quantity that we were taking the sine of, that expression, that argument, the exact same as the denominator. So we'll do the same thing again. So I'm going to say u is equal to 5x. Again, I notice that as x approaches 0, 5 times x approaches 0, that would make u also approach 0. So when we change this, we're going to have to keep track of that. I also know that I'm going to have to replace an x. So I want to know what x equals, and x equals u over 5. So let's come over here and change everything in terms of this new variable. So as x approaches 0, u would approach 0. This is going to be the sine of u, and this is 7 times x. And what is that? U over 5. Which I'm going to take this, and here's what I'm going to do with it. Let's take a look. I'm going to write 5/7 limit as u approaches 0, sine of u over u. Is that correct? See what I did? I took this and I flipped it over. So I multiplied by 5/7, or 5 over 7u. I pulled the 5 out front, I pulled the 7 out front, and I left the u in the denominator. So I had a sine u over u. Okay, I'll slow down and pay attention and make sure I get this right. This is 5/7. What's the limit as u approaches 0 of sine u over u? 1. So this limit is 5/7. Okay, does anybody see another way that we could have done this problem that would have made this one heck of a lot easier? Not the 5/7, okay, because you can't factor out the 5 out of here, but you can factor something else out to make it look more familiar. Okay, let me change colors here. What if I did this? What if I thought of that as 1/7 times sine 5x over x, and then I slid that 1/7 out here, and then I had this to deal with. 1/7 times this limit right here. Does this limit look familiar? We just did it. And if we already did it, we know what the answer is. So this limit would be 5. So 1/7 times 5 would be 5/7. Okay? Pretty nice trick. Any questions? Okay, let's take a look at the next one. Can you make any guesses as to what this is going to be? It is going to be 5/4. Can we think about how we would make that work out? Either way. It's not exactly like what we've already done. Okay, because in each of these cases we had a plain old x in the denominator. Now we've got a sine of 4x. There's a quick little algebraic trick that we could do to make it look like something we've already done. Yeah, that's an argument. Okay, it's stuck with that. It's 4 times whatever the angle was we plugged in, so there's no factoring that we can do there. Nifty little trick. It's almost like a conversion factor. It's almost like adding something in and then subtracting it out. But the only way to change a fraction into another equivalent fraction is to either multiply the top and bottom by the same thing or divide the top and bottom by the same thing. So how about we do this? Let's write this as the limit as x approaches 0. What if I were to take the numerator and divide it by x and do the exact same thing as the denominator? Again, this is one thing that's difficult about higher mathematics. Making something look more complicated actually makes it, in this case, so you can figure out what it is. Now I've got a quotient. Can I find the limit of the top and the limit of the bottom? And as long as the denominator is not a 0, we're okay. Well, what's the limit of this as x approaches 0? 5. And what's the limit of this as x approaches 0? 4. So the answer is 5/4. Again, this whole idea of taking something that looks unfamiliar and making it look more familiar, either through a substitution as we did in a couple cases, or by doing some algebraic manipulation, extremely valuable skill. Okay? Any questions? Okay. 2 more, and then we're actually going to be finding derivatives of trig functions. Let's take a look at this one. And I'm doing this first just as kind of an introduction. These types of problems are actually toward the end of your assignment. So these next couple, we might have to think about these for just a second, but let's look at this one right here. This is definitely not the same as the ones that we've done, because this says a tangent 7x on the top. Everything else that we've done was in terms of sines. We can write it as a sine, can't we? Okay, so let's do this. Let's rewrite this as the limit as x approaches 0. Let's write this as the sine of 7x over the cosine of 7x over the sine of x. We normally don't leave this as a fraction over a fraction, or let's at least think of that as a fraction. So I'm going to take this, I'm going to flip it over, and I'm going to multiply. So this is 1 over sine of x. I could take the time to rearrange these and put them underneath, or write them as one single fraction, but that's not going to be helpful here, because here's what I want to do. I'm not good. I haven't done any with a sine on the top and a cosine on the bottom, but I have done one with a sine on the top and a sine on the bottom. And because this is multiplication, could I not do this? Couldn't I do the sine of 7x over the sine of x times 1 over the cosine of 7x? Could I just switch places with the two of these guys? Still the same thing? Okay, now here's the cool part. Let's look at this one right here. And as ugly as that might look, can you evaluate cosine of 7x if x is 0? What do you get out of this if you plug in a 0? You get a 1. So this quantity is a 1. Closer you get to 0, let's evaluate it by substitution. There's no domain issue at 0. Let's just plug it in. You get a 1 on the bottom. So you have 1 over 1. So this quantity right here, that factor is a 1. So all I need to know is what's the limit as x approaches 0 of sine of 7x over sine of x. And our model for that is right here. Sine of 5x over sine of 4x was 5/4. So what's the sine of 7x over sine of x? 7. So this is a 7, and we could go through the same process that we did up above, but in any event, the limit here is 7. Because the cosine of 0 is 1. Good little thing to remember. People forget that all the time. Okay? Yeah, that unit circle you memorized in 1060, Good thing to know. Good thing to know. Okay? All right. Any questions there? Okay, let's take a look at the next one because I find this one really interesting. There are several different things that we can do with this. This has a cosine squared on the top and a theta on the bottom. Clearly can't be evaluated by substitution, as Preston will tell us if we, sorry, Weston. Yeah. I'm mixing your brother's name and your name together. Okay. If I plug in a 0, cosine of 0 is 0. Square that, I still get 0. Okay. Or sorry, 1. Square that, I get 1. So 1 minus 1 on the top is 0. I get 0 on the bottom. Okay. Sure. We could use a Pythagorean identity here. So use a Pythagorean identity here. And we're going to change this to... let's see, that was sine squared theta plus cosine squared theta equals 1. So if I move the 1 over here, it becomes negative. The sine squared over there, it becomes negative. So this would be negative sine squared theta over theta. And why is that helpful, one? Okay, so we've got one single term here that we're dealing with, and it's in terms of sines, which we've already dealt with quite a bit already today. Okay, how do we finish this though? Okay, so we're going to rewrite this as negative sine theta times sine of theta. And where am I going to put the theta? It doesn't really matter. I think it would probably feel a little bit more comfortable if we did that. Because then I've got, now remember, I've been doing arrows. I haven't been writing the limit, but I'll bring that back now. The limit as theta approaches 0. Well, the sine of theta over theta as theta approaches 0, this tends toward 1. Is there a domain issue with this one, or can I do this by substitution? I can do that by substitution. The bottom's a 1. I've got no domain issues there. If I plug in a 0, what is the sign of 0? Happens to be 0, so I get 0 times 1, so the answer on this one is? Answer on this one is 0. Okay. Any questions there? We could also do this. This is just a nifty trick, utilizing this limit right here. And this comes up quite often. Whenever you see something that looks like it might be a perfect square minus a perfect square, you can factor it into its conjugates. So this would be the cosine of theta minus 1, and then times the cosine of theta plus 1. And then the denominator is theta. Well, I could put it underneath the whole thing together, or I could just do this. Let's take that idea of working with these fractions. Let's break it up into two separate pieces. That looks like an h, doesn't it? Okay. And then we'll take the limit. The limit as h approaches 0. Sorry, theta approaches 0. What does that approach as theta approaches 0? 0. As long as it's a number, we're okay. So let's just make sure that this is a number. If you plug in a 0, you get a 1 plus a 1. So you get a 2 on the top, 1 on the bottom. 2 times 0 is 0. So in either case, you end up with 0. The nice thing about trig functions, especially when they're squared, or even when they're not, you've got all those identities that you can work with. So there are lots of different approaches that you can take. And as long as you get the same answer either way, should be fine. Okay, any questions? Okay. All right, we're now ready to actually find some derivatives of trig functions. And we're going to do this first one. We're going to do this one graphically. So we're going to look at this and we're going to think about, okay, let's graph the original function. So let's graph sine of x. Now remember, sine of x starts at 0 and goes up to 1 when we get to pi halves. So we're here, here, here. And I put this mark on here for a good reason. We'll take a look at that in just a second. And then we're at -1 and then back to 0. And it does the same thing on the other side. So it just repeats this pattern. So I'm going to try and draw this as carefully as I can. Good looking sine curve here. Arrows on the end just indicating that it extends forever in both directions. And then I'm going to change colors here. And we did this several times in the last few sections. We're going to take this graph So this is the original function, and notice that this is labeled as f prime. These are the slopes of the functions. Now, if I'm going to go from the original function and then graph what the slopes are, what are the easiest slopes to find? When it levels off, when it's flat, right? So that would be here, here, and here. So let's come straight down here, and I'm going to put a 0 right here. I'm going to put a 0 right here, and I'm going to put a 0 right here. Okay, we know the derivative has to equal 0 to each one of those places. Now, what do all of these have in common? As far as slopes go, they're all positive slopes. Even down here, again, we're not talking pre-calculus, and we're not talking function value. We're talking what type of slope does it have? Sloped upward, okay? We probably reach our highest slope about right here, our biggest positive slope, and then we start to kind of level off again. So we've got a small positive number, fairly big positive number, and then a small positive number right here. So roughly what would you say is this slope right here for this middle one right there? About 1. This is 1.5. The reason I put this on here is that would be about 1 unit. Pi divided by 2 is 1.57, so that's about 1.5. Does that look like it's roughly to scale? And if I were to go to this point right here and compare it with the origin, does that look roughly like a slope of 1? We're just taking a guess. Does that look okay? Okay, so we've got a slope of 1 on its derivative. Well, if I said this was a slope of 1, what slope do I need to assign to this right here? Better be negative 1. And what slope would I assign to this right here? Right there. Positive 1. Okay. Well, let's come down here and let's take a look at what we've done here. We've just graphed a couple of dots here. We were talking about how it goes from a slope of 1 right here to a shallower, a smaller positive slope. So maybe something about right there, maybe a 1/4 or something like that. But if I connect these dots with a nice smooth curve, or as close to a nice smooth curve as I can get, what does it look like? Looks like a cosine, okay? So in fact, the derivative of the sine function is the cosine function. So the derivative of sine of x is cosine x. And we're going to run through a really quick proof down here below. How many of you like the proofs? Or would you just say, a couple of you like them? Okay, so let's run through a proof. We're going to do them anyway. It wouldn't matter if you didn't like them. Okay. So, and normally when I do a proof, I'll give you a hint as to what's going to happen. We're going to use the definition of the derivative, so that's going to be the limit of the difference quotient, a sum identity, and then a familiar limit. So let's take a look here. So we're going to take the limit as h approaches 0, sine of x plus h minus the sine of x all over h. And again, the reason we like this format is because we're generally used to simplifying, and that's what we're going to be doing a bunch of here. So I'm going to draw an arrow instead of the limit. We'll just work on this algebraically. The first hint was start with the definition of the derivative, which we just did, and then use a sum identity. Sine of x plus h. Okay, using the sum identity for sine, that's going to be the sine of x cosine of h, plus or minus. It is plus the cosine of x and the sine of h, and then I've got this minus sine of x floating around here. All of that's over h. Any questions? Yeah, the way I teach this is I say, because these two are different, the sign between them gets to be the same as this one right here. You remember with this, the sum identity for cosine, it would be cosine, cosine, and because those are the same, this has to be the opposite operation. Does that work? Okay. So let's take a look at this and let's rearrange this. Now, you could spend some time manipulating this. We've got a limited amount of time today, so I'm going to just rearrange this for us. This is going to be the sine of x, the cosine of h, minus the sine of x. And the reason I did that is because those have a common factor. And then I'm going to write plus the cosine of cosine of x times the sine of h, and all of this is over h. Now, I could put it all over h, or I could say, you know what, I kind of like the two of these, so I'm going to put that over h, and I'm going to put this over h. Now, correct me if I'm wrong, because those have a common a common denominator. I could just put those together. I'd have 1h on the denominator and then those three terms that are represented here up there. Perfectly algebraic legal move, right? Ideas. What do I do with this? Factor out the sine of x. So I'm going to write the sine of x here, and then I'm going to write down what I'm left with, and this should look familiar. Then I'm going to write this one here, but I'm not going to write it down that way. And notice how I'm saving some space here to write some other stuff. I'm going to write this down as, tell me what I'm going to write. Cosine of x times sine of h over h. Because what is the variable in the limit? What variable is changing here? H is. So unless it has an h in it, for all intents and purposes, we treat it as a constant. So I'm going to change colors and I'm going to write really big. In the limit, does this change at all? For all intents and purposes, it's a constant, okay? What is this? 0, okay? So I have the sine of x times 0. So what does this whole quantity, this whole limit turn into? A 0, okay? For all intents and purposes, because h is the limit, it's the variable. What is this? Cosine of x. It doesn't change at all, okay? What about this? That limit is 1. So I've got the cosine of x times 1, so the limit is the cosine of x. So what we just did is we went through some graphical evidence as to why the derivative of sine is cosine. Then we went through and we proved it from the definition. Okay? Now, that took about probably 10 or 12 minutes to go through the two of those exercises. You could do the same thing with nearly every other trig function. I'm going to do this one really quickly. I'm going to graph the cosine function. So the cosine function, you'll remember, starts here and goes like that. Okay? Oops. Got that one. Get that in the right place. There we go. So it looks like this. And then we could run through and we could do the same thing. Now I'm going to do this in blue. So this is the original cosine curve. Now I'm going to graph its derivative. 0, 0, and 0. So it would be 0 here, 0 here, and 0 here. 0 again here, I suppose. What type of slopes do I have here? Negative. And this slope right here would be -1. By the same argument we went with on the last page, if we called those slopes positives and negative ones, okay, the same thing would be true here. And on this one, this would be +1. +1. Do the same thing here. So here's what I get. So if the red one is y equals the cosine of x, then the blue one would be, gosh, it looks really familiar. It starts at 0, goes down. What is this one? It's the negative sine of x. So negative sine of x, okay? And there's a proof. I think they actually have you do that as an exercise on number 20, but it's done in a similar fashion, okay? I'm not going to go through a proof for that one, okay? The graphic evidence hopefully is enough to make that argument for you and convince you, okay? I am going to go through a proof for the derivative of tangent, though, okay? And the hint here is find the derivative of tangent using the quotient rule and trig identities. Quotient rule and trig identities. So not from the definition. We're going to take this and we're going to say y is equal to, what am I going to write? Sine of x over cosine of x. That's exactly the same thing. So that means dy dx, that means the derivative of y with respect to x. The derivative of tangent would be, well, let's see here. Let's do some work on this. It's a quotient. You've got to have the quotient rule memorized by now. If you don't, you're in trouble at this point. Derivative of the bottom. Do you find the derivative of the bottom first? No. So whatever rule or whatever phrase you have in your head to figure it out, you better make sure that you know, I mean, the way I remember it is, it's the bottom, just the bottom. So bottom, blindly write down what the bottom is, times the derivative of the top. Derivative of the top is cosine, so this is going to be cosine of x. Make sure you have the minus, right? Okay. Then it's going to be the top, and I'm going to put that in parentheses, even though it might not be necessary here. This is going to be sine of x times the derivative of the bottom. Put that in parentheses. The derivative of the bottom, derivative of cosine is negative sine, all over the bottom squared. So this is going to be cosine of x, quantity squared. So then I take a look at this and I start cleaning this up. Well, cosine of x times cosine of x is cosine squared x. Negative sine x times negative sine x. I've got two negatives, so that's a positive. So this is going to be sine squared x. And the bottom is cosine squared x. Now, because I'm really good at algebra, I'm going to cancel that cosine squared with that cosine squared. Please, my gosh. I can't tell you how many times somebody's running through and doing the problem correctly, and then they'll do some stupid algebra mistake. They'll start making up their own version of mathematics, and they'll get it wrong. That is wrong. You cannot cancel a term with a factor. What's the right thing to do? Yeah. Fundamental trig identity, the Pythagorean identity, cosine squared plus sine squared of an angle is 1. So this is 1 over cosine squared, which we would normally write as secant squared. So the derivative of tangent is secant squared. Yeah.
Why is it plus?
Because it minus from the formula, minus from the quotient rule, and minus because the derivative of the bottom derivative of cosine is negative sine. Okay? Got it? Is a positive. Good? Okay, so I'm going to write down these derivatives again, and then I'll write the ones that we haven't derived. So the derivative of sine is cosine of x. Okay, and again, you got to put the argument in there. You should put the x there. This is negative sine of x. This is secant squared of x. Okay, and then I'm going to work my way backwards. Okay, the derivative of cotangent is negative cosecant squared. The derivative of secant is secant of x tangent of x. And the derivative of the cosecant is the negative cosecant of x cotangent of x. Okay. Do you notice any patterns? Any trig function with a co in its name is called a co-function. So cosine is the co-function for sine, and vice versa, frankly. Okay. Any one of the co-functions, what do you notice about them? They're negative. Okay. So the derivative of cosine is negative sine. The derivative of cotangent is negative cosecant. The derivative of cosecant is negative cosecant cotangent. Okay, and notice some of the symmetry here. These two are probably the hardest, but you'll get these down. You just have to get these memorized, unless you'd like to go through a 5-minute process of deriving them every time. Okay, and these two would be very nasty, believe me. Okay, although you could do these using the Okay, I don't care how you memorize them, but you've got to get them memorized. And now let's just run through and let's do a bunch of problems here. Okay, in order to do this problem, what rule do you have to apply? Product. This is a product. So when we find the derivative here, it's going to be, again, however you remember it, first times the derivative of the second, plus the second times the derivative of the first. And then again, we'd want to probably clean it up just a little bit. So this is going to be e to the x. I'd probably write cosine x minus sine x just because that looks a little bit better. Nothing else you can do there. How would you do this one? Okay, you're going to have to rewrite it as the sine of x times the sine of x. And use what rule again? Product. So we're going to have the first times the derivative of the second. So that's going to be negative. Oh, excuse me, cosine, just cosine. And then plus the second, which is sine of x, times the derivative of the first, which is cosine of x. So I get, well, even though they're different orders because of the commutative property of multiplication, I could write them both as a sine x times a cosine x. So this is going to be 2 sine x cosine x. It is. It's a double angle formula. Yep. And we'll actually see where that comes from. We'll find another way to derive that tomorrow. Yep. That's all you'd want to do with that. I suppose if you wanted to, if you're like Juan and you've really got okay, let's take a look at the next couple. Again, we had several problems last time where you could simplify quite a bit algebraically before you did any of the quotient rule or the product rule. Is that possible in these cases here? Probably not, okay? And this is when it starts to get really and it was like, I worked on that chapter and it just, I was just hoping it would go away. Here's where it comes back and you're like, oh, that would have been nice to practice those a little bit more or memorize them rather than have a cheat sheet that you worked with all the time. So when we find the derivative of this, and I'm going to write fairly small so we've got room for this, I need to use the quotient rule. So I'm going to take the bottom, just going to blindly write that down, times the derivative of the top. Derivative of tangent is secant squared. Minus the top, so tangent of t, times the derivative of the bottom. It's got a 1, so the derivative of 1 is 0. And then we've got a secant. The derivative of secant is secant tangent. So this is going to be secant t tangent t all over 1 plus secant t quantity squared. You don't just get to square the 1 and square the secant squared. It doesn't work that way. Okay, so please don't make that mistake. Okay. Do you see anything? I mean, we could just blindly go through and multiply through, but is there anything that we might want to do here? I've got a factor of 1 plus secant t. It would be cool if I could cancel that there. I can't. Okay, it's part of a term. It's not a factor all by itself. Okay, there's not one in each one. Okay, you can take a secant out there. So we can try that. Let's take out a secant t. Let's see if that works out right. So this is going to be, that means there's going to be one of these left. So that's going to be a secant t plus a secant squared t. And then this is going to be minus tangent squared. Now, the reason that might be advantageous is you'll remember from your trig class that there were several variations of the fundamental trig identity. Okay? So if you have a trig function squared, it's not a guarantee that you're going to be able to simplify it or rewrite it using the Pythagorean identity or a Pythagorean identity, but there's maybe a good chance. So let's take a look here. Let's think about what that was to begin with, and I'm going to write that over here. So it was the sine squared of x plus the cosine squared of x equals 1. I don't have any sines or cosines, but I do have secants and tangents. How can I make secants and tangents out of this? Yeah, divide by cosine squared, right? So that's going to be tangent squared x plus 1 equals secant squared x. We'll take a good look at this. Okay. You could do a couple of things. Here's what I'm going to do, because I think this would be a little bit easier. If you want to take the secant and write tangent squared plus 1 in its place, that's totally okay. Here's what I'm cluing into. This is secant squared minus tangent squared. What would happen if I just moved that over to the other side? don't I get a secant squared x that's positive and a minus tangent squared x? So what is this junk right here? That's just a 1. So here's what I've got. I've got secant of t. And again, by pulling that out, these would be cubes if that wasn't there. And cube trig functions aren't very nice to work with. By pulling that out, I've got something that I can work with. And then take a good look at this, and you can stare at it for just a second. We may or may not need to rewrite it. Do I need to rewrite anything? Okay. Because of the commutative property of addition, 1 plus secant is the same as secant plus 1. So I can cancel this with one of those. That means the only thing left on the top is a secant, and on the bottom is a 1 plus secant of t, of course. Now, I can probably leave it like that. If I wanted to change both of these into 1 over cosines and write everything in terms of a more familiar trig function like cosine, you could. If this is a problem in the back of the book, I would bet that it looks like this. Yeah. Right here? From here down to here? Oh, right here? Okay. So I took out the secant. Okay. So I took 1 out of here, and I took, let me cross them off. I took that one out, and I took that one out. Hold on. So I'm taking that one out. That's represented right here. Then I distribute this through here and here. So that's a secant. It's right there. That's a secant times a secant squared. And what's the only thing left of this one right here? A minus tangent and a tangent. So it's a minus tangent squared. Okay? If I skip any steps like that, stop me a little sooner and we'll make sure we're clear there. Okay? Good there? Okay. So you've got some problems that are like that. And let's take a look at this one. And I'll set this one up. I'll see if we can finish this. There's a couple problems at the bottom that I'd like to get to. Any simplification that can be done? Dang it, no, there's not. Okay? It would be really nice if we could simplify this, but I mean, we are stuck. Not only that, I want you to stop and think about this because this is the first time we've run into something like this. If I'm going to find u prime, it is the bottom, just blindly write that down, times the derivative of the top. Now, take a good look at the top. Don't say anything out loud. If you're going to find the derivative of the top, what rule do you have to use? You've got to use the product rule. Okay? So this is a product within a quotient. Oh, thanks. Thank you very much. Okay, got it? Okay, so watch. We're doing the quotient rule. I just wrote down the bottom. Now I've got to write down the derivative of the top. Now I'm going to put that in square brackets, and I'm going to think, okay, the way I remember it, first times the derivative of the second, negative sine of theta, plus the second. Well, that's good news because the derivative of theta with respect to theta would just be a 1. I'm going to write that just to make sure it's clear. See how we use the product rule there? Minus the top, theta cosine theta, times the derivative of the bottom. And what is the derivative of the bottom? Cosine of theta. Good? All over sine of theta plus 2, quantity squared. The calculus is over on that problem. We used the quotient rule and a product within that quotient rule to find the derivative. The calculus is over. Is that simplified to a reasonable degree? No, it's not. Okay? So we're going to want to look for ways that we can simplify this. We may end up multiplying things together and all that sort of stuff. We're going to come back to that one in just a second. Okay? Okay. Calculus is over there. The rest of that is just pre-calculus stuff. Okay. Now, I want to just quickly run through these, and then we'll come back up and do that other one if we have time. Notice at the bottom of the page, it says, expand this, then find the derivative. So you're going to multiply that by itself once. Take that polynomial, multiply it by that again, and then differentiate that. You're going to have a degree 3 polynomial. It'll have 4 terms. You just differentiate each one of those 4 terms. Okay. Let's do this one because this is kind of interesting. Everybody kind of likes this. We want to find, what does this mean? Fourth order derivative, okay? So y prime, cosine of x. Y double prime, negative sine of x, right? What about y triple prime? It's going to be negative cosine. And what about the fourth order derivative? Right back to sine of x, okay? So one of the interesting things about sine and cosine, because they are derivatives of each other, give or take a sign, if you continue differentiating, in this case, every 4 times that pattern is going to repeat. You're going to start off with sine, then get cosine, then negative sine, then negative cosine, then back to sine, and it would just go over and over and over again, okay? May be useful somewhere, okay? Let's take a look at this one. It could, yeah. I mean, if you wanted to take the time to memorize the pattern and how often do fourth order derivatives or 16th order derivatives come up and stuff like that. So let's take a look at this one. Product. First, secant of x times the derivative of cosecant. Now the derivative of cosecant is negative cosecant times cotangent plus, now it's the second, cosecant times the derivative of the first, which is secant tangent. Now, what do you think there? Simplified to a reasonable degree, slide the negative out front on the first one, or should we do something else? I mean, we could easily do this, right? This is secant, cosecant, cotangent, cosecant, secant, tangent. Ideas? There's a secant and a cosecant, okay, so we could pull those out, okay, that might be one thing to do. And we could pull out the sine too, I suppose, if you wanted to. That would be one thing to do. And then write down what's left. Negative cotangent of x, and then this would be plus tangent of x. Any other ideas? Let's try this. Okay, cosine x, sine x, cosine x, sine x, right? Plus sine x, cosine x, sine x, cosine x. Cancel here and here. Cancel here and here. Negative 1 over sine of x squared plus 1 over cosine squared of x. And what are each of those? That is a cosecant squared, a negative cosecant squared, and that is a secant squared. Okay? Lots of different ways to rewrite that. And that's not the only way to get there. Okay. Any questions? Okay, last one, and it looks like I'm going to leave the algebra on that previous problem for you. That'll be fun. Okay, let's take a look at this one. This should look, I mean, just slightly familiar. We did something kind of like this. Anybody remember this? What would you have to do this? Okay. So what you'd have to do is you'd have to group 2 of these together. Let's call that one the first and that one the second. So this is not a product within a quotient. This is a product within a product. Okay? Or it's a triple product. And if you remember how that triple product worked out that we did last week, this is a pretty quick problem. If you had to do the first times the derivative of the second, which is negative sine of x, plus the second times the derivative of the first, the problem with the derivative of the first is, when I find the derivative of the first, what have I got? I've got a product, okay? So I've got those 2 terms there to worry about, okay? All right, do you see how to do it? Okay, any questions? Okay. Projects, if you're done up here. Quiz on Thursday. It'll go up through 3.4. Tomorrow we're going to cover the most important differentiation rule. It's called the chain rule. Please make sure you find, multiply that out and find the derivative. That'll be helpful for tomorrow. Thank you very much.